Welcome to the Todd and Noah show. Noah, taking the mystery out of electric motors.
Yes, hello from sunny Tampa, Florida.
Oh, sunny Tampa, Florida. You moved.
I move a lot.
You're a mover and a shaker.
Yes.
So
that's the mystery.
That is the mystery. Well, I thought the smoke was the mystery in the motor,
we'll
but
solve that in our last conversation.
Well, we're going to fix it. We're fixing to solve it even more by diving into our. If you listen to our first introduction podcast, we were talking about the next in the series, which was power quality and how important power quality is. So maybe you can start and just give us like what governs power quality? Who decides?
Right.
And what is power quality?
That's a good question because a lot of people just want to know if there are alarms, if there are limits, who established those limits and how do we stick to them? Well, our favorite standard of reference is the IEEE 519. IEEE being the Institute of Electrical and Electronic Engineering. Okay. And they establish, they're well known and respected around the world, really. And them and IEC and a variety of things. But IEEE is a good reference. 519 does a great job in terms of breakdown of harmonic limitations. And so, as many, vendors would do, they look at some of the bodies of knowledge and the standards to build in their alarm set points, and we're no different. So a lot of our initial out of the chute, alarms that are established, come from that 519. Another standard is the IEEE 1159. It takes it a little bit, from being more of a dedicated power systems power quality evaluation to now more monitoring of the electric motor to some extent, and a little bit more of the testing side. So
maybe transients and
it actually gives you like a little bit more information on where you should test, that kind of stuff. Not just the the limits, but maybe a little bit more on the application of power quality troubleshooting and stuff like that.
So tell me what kind of data we should be collecting to analyze if we have power quality issues. What are we looking for?
And that's a good question. One of the things, because you always hear about harmonics, right? And that's that's something we don't want to miss. But for the most part, we look at the voltage quality, voltage imbalances and stuff, which kind of lean a little bit more towards the power circuit fault zone. But we certainly want to pay attention to that as well. But we're going to source from the voltage and the current distortion levels, and you'll hear us talk about harmonic voltage factors, and derating factors, things that are going to be affected by these harmonics, and of course, even some of the not just total harmonic distortion, but the total harmonic distortion of current, right, which is a little bit different. And we'll talk about how a leg, an individual leg in a power system may have different harmonics than the bus itself. But certainly we'll probably focus a lot on the distortion and the different levels of harmonics.
Now tell me, why do we need to care?
That's a good question. If you're a utility plant, they usually say, well, we make power. We don't need to care. Right? But what did we talk about in the first introduction? What was the biggest killer of motors?
I think it was heat.
You would be right. Correct.
I think it was heat.
And so this is no different, right? If power quality was just a blip on the map that you had to be aware of it and who was causing it, then that'd be one thing. But the reality is, with elevated power quality issues, and as some of the stuff I talked about in terms of harmonics and imbalances and things like that, it is going to increase the heat of a motor. And so much like almost every one of our fault zones, it does have a link to heat. And I like to use an analogy, and I should have practiced this analogy more. But like if we were in this studio room here, right, and let's say a fire broke out, and I was the only one here, I could get to that door pretty quick.
Yeah.
Right. But if I got you in here with me, which I do, and the fire broke out, you're not a small guy.
I would let you go first as a gentleman.
And I appreciate that. Because if you were in front of me, and there's almost no way I could get to that door at the same time. Well, think of power quality the same way. If you operate a motor under poor power quality, it has to work so much harder to accomplish the same task.
The same goal.
Exactly. So, again, it all relates to heat.
So now we go plus, we have positive, we have negative, we have zero types of harmonics. What do those do for us?
Good question. And when it comes to the breakdown of the positive, negative, and zero, it's a pretty simple walk down the math trail. But some of those aren't as bad as others,
Yeah.
right? And so if you think about positive harmonics, right? The first, if you're in America, you've got a 60 hertz. You know, if you're in a different country, you might be operating on 50 hertz, okay? And as that being the fundamental harmonic, right? So if you look at the even harmonics that follow that, like the second harmonic, the fourth harmonic, the sixth harmonic, right? These are all even, you know, multiples if you want to look at it, right? And so with that being said, they're actually moving magnetic fields around inside that motor at the same direction that your fundamental frequency is
Okay.
pushing around. So
They're just not as efficient.
that's the right word. So even though they're pushing the motor the same direction, they're not as efficient, and that's a big deal, right? So now the negative harmonics, right? And you know, you talk about the third or the fifth or things like this, and I shouldn't say the third; it'd be the fifth would be an example,
Fifth.
right? You know, those negative frequency harmonics actually oppose the rotation of the magnetic field. So it's like creating magnetic fields going the opposite direction, and as anyone can imagine, that's not very efficient.
No.
So that's a big deal. And then of course there's the zero sequence, which is always interesting, which is the, you know, the third harmonic, and let me see, from the third to be the fourth, fifth, sixth harmonic. I said I mentioned that as a positive, but it's not. It's a negative. It's a zero. Now those zero sequence harmonics tend to add up on the neutral and create a lot of heat, right? So people have to change the size of their neutral bus and things like that to overcome those zero sequence, because they tend to collect back at the transformer, right? So knowing all those positive, negative, and zeros, and knowing which ones you're dealing with will help you kind of make the good decisions afterwards.
So having a data set that actually goes out to, say, the 50th harmonic can be helpful, because it can start to say, oh, well, we have a lot of activity at the 20th or the 5th or the 7th or wherever it might be.
Right, and sometimes those higher harmonics are indications of a variety of different problems. And even if it's not a synchronous harmonic, let's say, to the fundamental frequency, you might start to see things like shaft line currents and stuff on the higher harmonics. So we do like to look out there a little farther and see if there's some stuff going on.
So what creates this on the distribution system? How is it how do harmonics get created? Tell us.
So the big creation, we like to call it nonlinear loads. It's kind of a big word, but it just means that when you're dealing with stuff like, you know, lighting, fluorescent lighting, computer systems, any type of electronics, they're not having your current is not effectively synchronized with your voltage in a lot of situations, and as a result, we call that synchronous or, nonlinear loads. Current's not going up at the same rate.
Computers, your desktops.
Right, and one of the biggest that I didn't cover is VFDs, right? A very popular thing in the industry today. So for those of you who are installing VFDs, and a lot of us are for reasons of efficiency and cost savings and actual process, controls.
So you mentioned VFDs. What are the benefits of a variable frequency drive?
VFDs are, the benefits are quite big, and so a lot of it's in the process control and the ability to change speeds at will and do it efficiently, and with a broad range of frequency controls, actually. Additionally, I would be remiss not to say that the impact of VFDs on motors is in part it reduces a lot of the stresses that motors go under in terms of the inrush startup, right? It's a controlled startup of the motor. They're slowly ramping up the voltage. This is a lot less stressful on a motor's life. And of course, if that's to be true, then money comes into play, right? The money man, the bean counters, as we call them, whatever, they're going to play a role in the benefits of VFDs as well.
So what are the different types of variable frequency drives that exist in the industry today? Can you talk about those?
So for those of you who were involved early in the drive, industry and the manufacturing, a lot of times what you were seeing was a current source or a voltage source drive, right? So they're controlling the current to get the output signal that they want, or they're controlling the voltage to get the output signal they want. And then the one that's far more popular today, for efficiency and a variety of other reasons, is the pulse width modulated drive, which is really what we see more often.
That's the majority of industry. Now, how do we test those? How do you test a variable frequency drive or a VFD?
So you know how when you drive into an oil shop to get the oil in your car replaced, they usually give you the good, better, and best plan?
Silver, bronze, platinum, or
maybe.
Bronze, silver, platinum,
That's the one, right.
Or gold. Silver, gold, platinum.
That's the one, right? So we offer the same approach to VFD testing, or motors that are operated by VFDs.
The good, better, best.
The good, better, best. And a good approach would be to check the line side of a drive.
Okay.
Right? And then this is not an unimportant part, because by checking the line side of the drive, you get an idea of what power is being sent to the, remember power quality, what power is being sent to the drive. Is it good? Is it healthy? You know, and then of course it gives you an idea of what is the drive system reflecting back on the power system, which is can be a problem, especially if you're like a, you know, a chip manufacturer. You need precision power quality. You can't have a lot of noise and stuff coming back up on the distribution system. So that's the good line side of the drive. Better would be the load side of the drive. Why do we like it better? Well, because now we're seeing what power is being delivered to the working part of the system, which is the motor, right? So you get a chance to see the drive and the motor, and that would be the better approach. You're going to see a variety of things. We mentioned the standards earlier. Well, the standards are all written for a line side, you know, for the most part, line side of the drive. So as we start to test down on the load side of the drive, recognize that the standards do not apply, and you'd have to modify the set points in your alarms because they're completely different, and of course, every output of the drive is different from one versus the other. The load can have an effect on that as well.
Okay. Now the best.
The best, right?
What's the best way?
Is real difficult. It's both. Right? It's both the line side and the load side. If you can get them both, you're doing yourself a big service.
Okay. Now, is there any type of special insulation requirements on a variable frequency drive, especially pulse width modulated, because of this rapid firing sequence and absorption current rates on the insulation? Do we have to have different type of insulation? It is highly recommended.
There are some things that can be done. We'll talk about that, but certainly it takes some manufacturers. I know for instance, Baldor, right, as a motor manufacturer, they were advertising at some point that every motor over 1 horsepower, you know, was going to get what they called inverter duty wiring, right? So inverter duty wiring is highly recommended. You're going to see it in, you know, coming out of the NEMA requirements and all that kind of stuff. If you're dealing with transients, which we'll see out of a pulse width modulated drive, these are rapid rise times, voltages, you know, reaching almost 3 pu or per unit, you know, so 3 times the phase-to-phase voltage as quickly as 0.1 microseconds. That is a extremely fast rise time of voltage that can absolutely do damage to a standard Class B insulation system, let's say that's not inverter duty. So yes, inverter duty wiring is highly recommended. If you're modifying a system and adding a drive to an already existing system, then it becomes real critical to understand what kind of transients that older insulation system. It may last 3 weeks and you're out.
Getting back to the insulation side of things, you know, one of the reasons that you want to look for harmonics, right, is especially on the front end of the drive, is you want to verify that they're not spitting harmonics back out onto the distribution system that may go to a motor that doesn't have this type of protection or this type of insulation, correct?
That's a very good point. And we talked about the good plan, the line side analysis. And I used an example, like I said, a chip manufacturer or, you know, some medical industry that has to be super critical on the clean power. So various drives cause various problems. Remember I mentioned all the benefits of the pulse width modulated drive, you know, better control, better frequency, you know, variability, you know, in fact, overall just better control, right? And in fact, better efficiency. That's right. So, you know, the cost to run a pulse width modulated drive is always going to be better. But there's always, with every positive, there comes some negatives, and the pulse width modulated drive does create a few more harmonics, right? Because they're rapidly changing basically the width of the pulse coming out of that drive from a skinny pulse to a fat pulse, and that creates that synthesized sine wave. Well, all that activity creates quite a bit of harmonics, and they'll all run back to the power system, right? So one thing to keep in mind, I mentioned that the dedicated leg versus the main bus. The dedicated leg can have very high levels of current distortion, can have very high levels individually, but when you back up to the bus, a lot of times that disappears naturally. So it's important to know that if you're on a dedicated motor, you know, a leg of the bus, you might have 20% current distortion levels, which seem really bad, but you go one leg up and it drops to 2%. Right? And so it's important to recognize that the effect it has. Most standards, as we mentioned, the 519 standard, focuses heavily on the voltage distortion. So another thing to keep in mind is that voltage is shared equally amongst the bus, amongst the distribution, you know, system that you're on. But current changes from line to line. Okay, so that's something to be aware of as you're troubleshooting motors. Expect big changes in your current distortion, but once you get on a given bus, the voltage distortion will be shared throughout the system.
Gotcha. So now let's say that we come across some harmonics on a specific motor or on the bus or on the distribution system. What can we do? What do you do?
That's a good question, and there's very specific recommendations. They've got line reactors, filtering, capabilities, basically. And this becomes important, like they've got line side filters and they've got load side filters. Why would they have two? Well, the line side filters are really to protect the motor from voltage transients and things that occur. And have you ever heard of nuisance tripping?
Oh.
We hear it all the time.
We hear it all the time.
So with nuisance trips, a lot of times that's going to be line side driven. So what happens is the drive itself is sensitive to voltage transients that could occur for any number of reasons. There could be a capacitive, switching of the distribution system that sends a spike down the line, and if the drive sees that, it'll shut down on an over voltage transient. Well, no one wants to lose productivity because they're switching capacitors for reasons of power control. Right? Yeah. So that's a big deal. On the load side, of course, you're trying to protect the motor from the various power quality issues that are known to come out of the drive itself. So
what you're saying is just try to filter them off of the distribution system so that they don't, because at the end of the day, they create heat, right? So they go in, create excess heat, they do extra work, but they're not efficient in how they do it. So we want to eliminate that. So that's why go on the distribution system, put the filters on there to try and get those off the line to protect your motor.
And in fact, how we said good, better, best, line side, load side? Well, if you're troubleshooting, a system and you suspect a power quality issue, and you have line reactors on the line side, where would we want to test? We want to test on the line side of the reactor and the load side of the reactor. These things are and will fail. And you'd hate to think that you're delivering poor power quality on a single phase of the drive to the motor, and all you have to do is replace a reactor. So be aware that if you've got line reactors and load reactors, that's going to add to the test points for you to take to make sure you're troubleshooting the entire system.
So Noah, we told you last time on our first that we were going to challenge you. So I'm just going to give you a set of descriptions here of what an individual came across, and maybe you can help us to start troubleshooting. This was a group of 4 motors, all in a line at a municipality, about 460 volts, large motors. I think they were 450 horsepower at 460 volts, so these are pretty massive vertical motors. And what drove them to think that they may had some issues, it was vibrating. One of the machines was vibrating terribly at a specific frequency. These were all variable frequency drive controlled. Now, they went to the manufacturer of the drive, and the first thing they said was, test the resistance to ground.
Test the insulation of the motor.
All right, so you can verify the zero reference. Now, they did that. The numbers were great. They were, and we're going to get into this with the insulation system, but they were well above IEEE 43 standards for insulation. So what would you recommend doing if you could, knowing you had 4 motors, and one of them was exhibiting an issue at a specific frequency? How would you go about determining what to do next?
Right, it's a good question. And to fully understand, I think it's important to understand why a drive manufacturer might, as some people say, try to send you down a rabbit trail after the motor installation. It's almost like they're trying to, the Heisman move. They're trying to, just hand off the troubleshooting to another, not their drive. It's not our drive, right? Yeah. But in reality, the drive manufacturer has reason to be suspicious of that. It doesn't always pan out. But in
this case, it didn't.
It didn't, right?
The resistance to ground was fine.
Right, but it's worth knowing if the ground system of the motor that's being supplied by a drive ends up being, intermittently grounded, that really can throw the control side of the drive off, and as a result, the drive doesn't run in a good way. It may start to cause, operational changes that are actually very detrimental to the drive. Okay, so that's important to know that there's a reason behind that. But if it was me, one of the things I like is when you said you have 4. Right. Yeah. First of all, which one of these is not like the other?
That's Sesame Street, old school.
That's right. That's it. But it still applies today.
Bert and Ernie coming in.
That's it. And it still applies today. If you've got comparisons, let's do it. But if they're complaining about a certain frequency as they're changing the, from a pump perspective, you change the speed, you change the load, right? Yeah. You're moving more water, I suppose. And so in that situation, I want to.
So it's ideal to compare.
Absolutely. I want to duplicate that frequency. Let's see when it occurs.
47 hertz on one, 47 on the other. Let's see what we get. Right. Picture's worth 1,000 words, right? Yeah. So on the one, we did a number of them. On the one problem one, we went to the actual, they went to the specific frequency that had the most vibration. And the variable frequency drives the output of the voltage. is, as you said, that's firing almost looks square wave-ish.
Right, it is very square wave-ish, yeah.
In this case here, what they found was one pole, instead of firing in the negative direction, actually fired in the positive direction when it should have been in the negative. Would that cause any disruptions?
This is a big problem.
That's a huge problem.
Yeah, so in general, if you're picturing this, you got like, transient square wave on the positive side, and then it switches to 0, and then transient, different varying widths on the negative side. Well, if you're firing the opposite of that, like let's say it's supposed to be firing negative and you're saying it fires positive, it's like an electronic brake or an electric brake. And electric brakes are very strong. So it makes sense now that when you talk about, getting every half cycle, getting a brake action, you can see where the vibration's coming from.
Yeah, and in this case, they were able to go back to the drive manufacturer and say, listen, it's firing in the wrong direction at the wrong time. So can you come in and take a look? And so this is where you first came up with your protocol, right? Your communication protocol that you talked about in the introduction. This is where the value of that comes in. The insulation system is good. However, power quality is not good because I have a signal firing in the wrong direction at the wrong time, creating this vibration. I need you to come in. That's so much more power than just to say, it doesn't work.
Right, a description is one thing, but actually evidence to the such. And a drive manufacturer seeing, that sine wave that you're describing, it's a slam dunk. It's going to end up being a phase card replacement. It may be and one of the things I always like to brag about in terms of electrical testing is often our testing is done in a nice air conditioning MCC. So this troubleshooting,
that's not so bad.
It's not so bad, no, especially in Florida.
Especially in Florida.
So yeah, a card replacement and this drive may be back up to normal. You hope that it hasn't created any damage to the motor. And this would be something you almost want to say, hey, let's get the mechanical group involved and say, hey, we've been cycling
especially
this
that
thing.
Much vibration.
Oh, yeah, this is a big motor to be vibrating that much. And like I said, electrical brakes is a rapid torsional change. I would be very concerned about the bearings. I would elevate the frequency of testing and make sure that we think this system is healthy.
Right, and so to bring out some other key points on that, the fact that you had a like motor to test is invaluable.
It's absolutely some of the best evidence you can have. And these were, in my impression I get is these were absolutely identical motors.
Yeah.
Doing the same thing. And you can't ask for a better comparison. A lot of people overlook that, but if you got two like motors, man, that is sometimes your number one tool.
Well, Noah, I thought I was going to trip you up on this one, but
like
you're too smart for us. As always, we appreciate your technical expertise, the knowledge that you're giving to us.
Thanks again for letting me share.
And we're actually, as well, very happy that you tuned in and listened to us. We're going to be, the next podcast that we're going to talk about is, we wrote this down and said, we're going to share with you how you can help increase or maintain your motor efficiency through the power circuit.
And is efficiency important?
Efficiency is highly important.
So you don't want to spend too much money on power. You don't have to.
Yeah, so you don't want to miss this next podcast that we have coming up on the power circuit. And we're going to tell you what the little thumb rule is on a study that was done with respect to power circuit and efficiency, and we'll discuss that when you come join us on our next podcast. Until then, I'm Todd Gunderson, Vice President of Sales and Marketing for PDMA Corporation. This is Noah Bethel, the Vice President of Product Development. And as always, we appreciate the time that you've spent with us, and we hope you come back and see us real soon.
Thank you for joining us for this episode of the Todd and Noah Show. We'll be back for another episode very soon. In between, we hope to see you in the Mobius Connect online community where you can network, learn, and share with Todd and Noah and other industry professionals at mobiusconnect.com, and we will see you there soon.